Hello and welcome back to another LeetCode problem. Today we're going to be doing problem of the day for March 26th, Stone Game 2. And so this problem says, Alice and Bob continue their games with a pile of stones. There is a stones 1, it's a lot easier though. So this one is, there are a number of piles arranged in a row and each pile has a positive integer number of stones, piles I. The objective of the game is to win the most stones. They take turns, initially m equals 1. On each player turn, that player can take all the stones in the first x remaining piles, where x is between 1 and 2m. Then we set m equals max m and x. And then the game continues until all the stones have been taken. So let's take a look at a couple of examples and try to figure out what's going on. Okay, so first we have this one. And then, so what Alice can do in the beginning is x equals 1, and it shows you Alice can take 1 or 2. But if Alice takes 2, what would happen, right? So if Alice takes 2, then Bob can take all of this. So that could be one case, right? If Alice takes these two, then Bob takes these 3, because m would become 2, max m and x, right? So if m equals 1 in the beginning, Alice takes these 2, m becomes 2, and then you can take up to 2m, so then Bob would take those. So in that case, Alice would have 9, Bob would have 17. Okay, well let's say the other case. Let's have Alice take 1, so now Alice's score would be 2. Now Bob can either take 1 or 2. So if he takes 1, then if he takes 1, then Alice can take these 2, and then he'll take the 4. So clearly the better choice is to take 2 and let Alice take the last 2. Right? So if that's the case, then Bob would take something, and then Alice would take these last 2. And so Alice's score would become 10. And that's the optimal solution for this problem if both people play optimally. Because if Alice takes 2, then Bob just takes the rest, and then Alice's score would be 9. So that's kind of how this problem goes, is each player tries to... It's a zero-sum game, so to maximize your score, you can also minimize the score of the other player, right? So the less that Alice takes, that the more Bob will take, and so on. So you're not only trying to minimize your score, or maximize your score, you're trying to minimize the score of the other player. And so what variables do we need? Well, we need this m variable, right? So that's 1. We also need to know whose turn it is. And then we also need to know what index we're on. And if we just brute force this, how many different states can we have? So m can go up to the length of this whole array, right? Because it can keep doubling, which would be, let's just call it n. Then whose turn it is would be 2. And I, the index we are at, is also n. So this would be 2 unsquared, I believe. Someone can correct me if I'm wrong on this one. And believe it or not, there's not too much simplification you can do in this problem. The only thing you can do, if there are these 3 states, the only thing you can do is you can simplify a little bit with memoization, right? Because you can end up in the same location. Because assuming you're here, let's say, if you know what m is and you know what I is, it doesn't matter how you got here. Or if you know what all these, so the turn. If you know what all these 3 variables are, and this variable would be, so if you know these 3 variables, it doesn't matter how you got to the state. You could have got here in multiple different ways. But this solution is a unique solution, and then the final solution would be when we are at the length of the list, in which case we would just return 0. But if you can recognize that it doesn't matter how you got here, when you are here, there is a subproblem, then you can recognize that this is a dynamic programming problem. And so we're actually going to do dynamic programming here, and we need to figure some things out, right? So the main things we need to figure out is, we need to figure out, okay, well, we are trying to get Alice's score, but Bob is also playing optimally, so it would be kind of tricky, right? How do we figure out Bob's score? Well, what we could do is Bob can simply try to minimize Alice's score. So we could have some kind of turn variable, and if it's Alice's turn, right, so if turn equals Alice, then we try to maximize the score. But if it's turn Bob, we can try to minimize the score for Alice. So we're going to keep track of only Alice's score, but depending on the turn, we're going to have two different goals. Because if Bob tries to minimize the score for Alice, then his score gets increased, right? Because like let's say there's some sum of this whole thing, Bob's score is the sum minus the score for Alice. So by minimizing this, he maximizes his own score. So we're only going to keep track of Alice's score, and that's important. And the other important thing you need to recognize is how to actually add these things up correctly for Alice and Bob, because it's going to be a little bit tricky. And so I definitely made a few mistakes with these, and I got some negative numbers, and it took me a little while to figure out exactly what's going on here. But that's going to be kind of the algorithm, is we're going to go through each thing, and we're going to ask who are we on, and then depending on who we're on, we're either going to try to maximize the score or minimize the score, and then we're just going to use dynamic programming to get the score from here. Okay, so let's try to code this up, and I'll explain it as I go through it. So first as usual, so we're going to do a top-down dynamic programming with memoization. So let's make a visited, or hash that as usual, standard for memoization. Now let's have a def dp, and remember what variables we need, right? So we need the index, we need m, and we need, let's call it turn. Okay, and so our base case is if the index is greater than or equal to length piles, that means we are out of bounds, so there are no more stones. So we can just return 0 here. Now our other usual case in memoization is we check if this is in visited, right? So if index m turn in visited, return visited index. And when you're not sure if it's a dynamic programming or there is some better solution, you can try to code it up in dynamic programming, and it should be pretty fast for most problems. And then you can see if you get a time limit exceeded, and can you optimize it, or do you have to go deeper? So that's kind of a hint you get. Okay, and now we have to figure out what are we actually doing. So remember that for Alice, we're trying to maximize the score, and we're going to be guaranteed, as long as we're not on the output, we're going to be guaranteed to get some kind of result that's greater than 0. So we can just say if turn, let's just say Alice is 1 and Bob is 0. So we can write that down. So Alice equals 1, Bob equals 0 as far as the turn. You can also just use a Boolean instead if you wanted to. So if this is Alice's turn, we're going to have res equals 0. Else, remember for Bob, we're trying to minimize. So by trying to minimize, let's make the res really big, right? And we're guaranteed to have it lower than this because we are not going to be out of bounds. Otherwise, it would return here. Okay. Now, how do we need to be looping, right? That's the other question. So we can loop anywhere from 1 to 2m. Now, this 1 to 2m, so 1 is actually the index we're on. So let's say we're on this index, 1 would actually take this pile. So we're actually going to be looping from 0 to 2m minus 1, because let's say m is 1, then 2m would be 2, and then minus 1 would be 1, because if we're here, this is already 1, and so the most it can ever be is 2, so that would be 2m minus 1. Okay, so let's code that up. So let's just call this x, right, in range. And then that's going to be, what did I say, 0 to 2m minus 1, right? So 2m minus 1. This is actually going to be the 2m because it's going to be the 2m minus 1 automatically. Okay, I think that should be right. So now what do we need to do? We need to figure out what's our output. We also, by the way, so as we're looping, there's one more thing, especially for Alice. So we're trying to figure out how many rows to use. But let's say we use this row, then we use this row, then we use this row, then we use this row, and so on. We're going to add however many rows we use to Alice's score, right? Like if we take 1 row, it's going to be this. If we take 2 rows, it's going to be this, and so on. And what we don't really want to do a sum of this, and then a sum of this, and then a sum of this, and then a sum of this. So what we want to do is we want to just have a total variable, and then we can just keep adding each row. So that's going to be pretty straightforward. So let's actually add that in here. So we can just say, we can say total, or we could say stones or something. Okay, and then so we need to add that in here. That's going to be piles x, right? Now we need to figure out, okay, if it's Alice, so let's just say if turn equals 1, and that was Alice. Then how do we calculate Alice's increasing score? So let me get rid of a couple of these. But let's say we are here. What we need to do, and we are only using this, then we say, okay, let's take this total and then the maximum starting here, right? Or, this total and the maximum starting here and so on. So it's going to be res equals, remember we're trying to maximize res, so total plus, and then the dynamic programming of, now where are we going in this index? So it's going to be index plus x, I believe, plus 1. Right? So x starts at 0. We need to go to the next index and the next. Right? So that's going to be that. And then m is going to be, so let me see here. Yeah, so this x value should actually be increased by 1 here, right? So it starts at 0. So it should be max of m or x plus 1. Yeah. Okay. Now we need to alternate the turn. So we can just say, let's say 0 if turn equals 1, else 1, something like that. Okay. So that's what we need to do for Alice. That's how we maximize her score. Now let's think what we do for Bob. So for Bob, we need to minimize Alice's score, right? And so we're not minimizing, like, let me go back here. So let's say we're here for Bob. What we need to do is we need to figure out something to take, not to minimize the current score we're at, but the current score after we actually go to the next part. So let's say we take this. We need to minimize the score of dp of whatever index this is. And we don't really care about the total we add to Bob because we don't care about Bob, remember. Bob plays optimally by minimizing Alice's score. So we don't need to add the total. We're just going to minimize the next dynamic programming place from the next index. And so let's write that in. So res equals min res. We're not adding in the total because the total is only going to update Bob's score and Alice's score doesn't get affected. Right? So index plus this is the same. Then this is the same. And this is the same also, actually. So let me just make sure that these parentheses. What did I screw up here? So this is that. Okay, so this needs to be here, I believe. Yeah, so same thing, 0 if turn equals 1, else 1. Okay, that looks right to me. Okay. So now we get this res. So this is Alice's score after this part we're at. So like I said, if we're here for Bob, this is actually Alice's score after we take something for Bob. So let's say we take this is Alice's score starting from here. And that's going to be minimized when it's Bob, and it's going to be maximized when it's Alice. So we can just add all these up. So now we need to put it into our array or into our memoization, right? Okay. And so pretty much let's go back at this problem and look at this first part and kind of ask ourselves what it's saying. So Alice takes the first one, right? So Alice takes here. So it's saying, what is Alice's maximum score starting here, going to some index, and then getting the DP of that. So it's going to be this plus the DP at this index for Bob. Yeah, right? Yeah. And then Bob here is going to be, what do I take? That's the minimum for Alice, and it's going to be this, and then the minimum for Alice is going to be this. So we're taking this value plus DP of starting here, which is 10, right? And this is Alice, so this is Alice, and this is Bob. So hopefully that makes sense. Okay, so now we do visited. Let's see what we got here. So we got index m turn equals res. Then we just return res. And I think I've done a lot of these dynamic programming problems with memoization. So it's just, once you remember this format, you can actually write these out pretty quickly. Remember, you need a visited hash set. You need some kind of base case. Then you need to check, is it in my visited hash set? And then you need to figure out some kind of actually dynamic programming recurrence relation. Then you just put in your value into this visited and return it. Okay, so now we need to do return dp. We start at index 0, m starts at 1, and it's Alice's turn to start, right? So let's try that out. Okay, let's see what we got. So this total should be stones. Okay, let's see. So we got 11. So we're off somewhere. Let's double check. And what do we get here? We got 5. Okay, so let's see what we did wrong here. All right, so, and it's very easy to screw up in one of these maths as well. So if index m turn is visited, yeah. Okay, we passed in m. By the way, m is 1 in the beginning, yeah. Okay. So if turn equals 0, if turn equals 1, res equals 0, yeah, that's right. Okay. Stones equals 0, yep. Okay, so it's going to be piled. Oh, we forgot one thing actually. So the thing we forgot is what happens. Yeah. So we are iterating through this thing, but once again, let's go back to this initial problem. So let's say Alice takes here, and then Bob takes here. But let's say he takes 2, right? Let's say he takes both of these, which he will. Now Alice can take here, and Alice can take up to 4. So we're going to try to take this one, we're going to try to take this one, but then we're going to try to take here, and the problem is that we are going to be out of bounds. And so we can't take there. So we need to, once we're out of bounds here, I don't know if that's the only problem we have, but once we're out of bounds here, we're going to need to break. And so we can do that. So we can say if, and what would this be? Index plus x, I believe. Yeah, is, and then what are we doing here? So we are saying this, if this is greater than or equal to length piles, then we break here because we've gotten too far. Okay, so that's not the issue though, but that's one of the issues. Okay, so for x in range 2 to the m, so let's see if that's right. Okay, so like I said, the biggest can be 2 to the m minus 1, so that should be fine. Okay. Stones plus equals piles x. That should be fine. If turn equals 1, so it's going to be stones plus dp index plus x plus 1. That's fine. And then this is going to be max m x plus 1. That's fine. Okay, and this is min res dp index x plus 1. Okay. Okay, so I did find the problem here, and the problem is this, that we are checking at index x, but we need to actually check at x plus whatever index we're at here, because we start at this index and we need to add x. So let's try that. Okay. Okay, so let's try to let's try to do the time and space complexity actually for this problem, and then we're going to be done. So remember that there's list n of these indices and there's list n of these piles, so it's going to be n squared here. There's n squared states, or 2n squared, but n squared. And then also, what are we doing? So we actually do have a for loop in here that can technically loop to the end of the array. And so this would actually be n squared times another n, right? Because we're going through this m. So it's like n times m, and this m can be up to n. So it's actually n squared times n, which would be n cubed. So it is quite a big problem, but I don't think you can make it any simpler. And we are already doing the sum thing, so we're saving some time there. Okay, and then space. So this is just how many states we have in the visited array, which would be n squared. And the most we can ever recurse down is n times, so that would be less than this, right? Because we can go like from here to here to here to here to here, which would be n times. Okay, so that's it for this problem, and if you like this problem, like and subscribe, and I'm going to make more in the future. So thanks for watching, and I'll see you in the next one.